poster. What we were interested in these experiments was whether or not changing the spatial frequency of a cue could influence both the saccadic reaction time, so the time it takes to program and execute an arm movement, and the speed at which you can covertly orient attention, that is, orient attention to a location you're not actually looking at. Now, we know that changing the spatial frequency of your cue does change saccade latencies. So as you increase spatial frequency, you slow down saccadic reaction times. A number of theories of attention argue, for example, premotor theory, oculomotor readiness hypothesis. These theories argue that covert orienting of attention depends upon saccade programming. So anything that changes the metrics of saccade programming should also impact on the metrics of covert shifts of attention. So if changing the spatial frequency of a cue slows down saccade latencies, it should also slow down the latency of covert shifts of attention. Now, covert exogenous shifts of attention take around 120 milliseconds to fully deploy. Okay, and that figure is based on research by Cheal and Leung and a number of other authors in the 1990s. So what we hypothesized was that if we change the spatial frequency of a cue, particularly if we increase the spatial frequency of a cue, what we should do is delay the point at which attention is maximally oriented. Yeah, so it should take longer to fully deploy attention into the periphery. In our first experiment, we tried, we tested this using 3 different spatial frequencies, 1 cycle per degree, 4 cycles per degree, and 8 cycles per degree, using a speed discrimination task using a standard Posner queuing task. So the participant fixates, you can see here, peripheral cue appears, and that can either be 1 cycle per degree, 4 cycles, or 8 cycles per degree, and then this low spatial frequency target appears. And participants have to make a speeded discrimination. And what you expect, of course, is that performance should be faster at the cued location than the uncued location because they've oriented attention there. What we predicted was that as spatial frequency increased, the SOA, so the duration between the cue and the target at which the queuing effects were maximal, would also be later in time. So we predicted that perhaps at 1 cycle per degree, the effect should be maximal about 120 milliseconds, but at higher spatial frequencies, you might expect that maximal point of attention allocation to be later, perhaps 150 or even 180 milliseconds. However, we didn't find that effect. So what we actually found was that although overall changing the spatial frequency of the cue reduced the queuing effect, okay, so lower spatial frequency cues produce larger queuing effects than high spatial frequency cues, we didn't find any effect on the time course. And in fact, what we observed was that covert shifts of attention were very, very rapid. So they occurred at our earliest SOA, which is 30 milliseconds, and they were pretty much the same size throughout. So we didn't see any evidence in this experiment of a gradual accumulation of attention at the cued location. Instead, it seemed that attention arrived at the cued location very quickly after cue onset and pretty much stayed there until the end of the experiment, apart from this little this odd little effect here, 120 milliseconds. Okay, so this is kind of surprising because the idea that attention gradually accumulates over the first 120 milliseconds first 120 milliseconds after a cue presentation is really well embedded in the psychology literature. So, but there are some pretty big, or 2 actually, major differences between the study we did here, where we didn't find any evidence of gradual accumulation of attention at the cued location, and the studies of Cheal and Leung and others, where they did. Those 2 differences are, firstly, Cheal and Leung used unspeeded discrimination tasks. So participants had as long as they wanted, and they used response accuracy as their dependent variable. The second really important difference is that Cheal and Leung only used valid cues. So in their experiment, the cue appeared and the target always appeared at the cued location. They didn't use any invalid cues at all. And that's a bit problematic because we know that as SOAs increase, you get alerting effects which produce faster reaction times and better discrimination accuracy. Okay, so there's a real risk, I think, that in Cheal and Leung's original experiments, what they're seeing is an alerting effect, not spatial attention. But to prove this, we did a second experiment. So in this experiment, again, we used three different spatial frequencies. I'm only going to present the data from the 1 cycle per degree, so the low spatial frequency, because that's closest to what Chiu and Leung did. And rather than doing a speed of discrimination task, we asked participants to do an unspeeded discrimination task. So this is much more similar to Chiu and Leung's experiment than experiment 1 was. And again, it's a very simple Posner queuing task. So there's a fixation point, a peripheral queue, and then a target appears. In this version of the task, the target is then masked, and the person has to make this difficult discrimination about the orientation of the grating. So what did we find? Well, this figure here shows the percent correct responses. And if we first look at only the valid condition, what we see is a gradual increase in performance that asymptotes around 120 milliseconds and is then fairly static. Okay? And that looks almost identical to the data reported by Chiu and Leung. So in fact, this is the data from their paper here. It's a bit difficult to see because it's all a bit small, but what you see here is a gradual increase in performance to around 120 milliseconds, then it flattens out. Okay, so data from our valid trials looks exactly like that of Chiu and Leung. However, if you look at our invalidly queued trials, what you see is that in the invalid condition, there's also a gradual improvement in performance up to around 120 milliseconds, which then drops off. Okay, so what we're seeing here is that at the unattended location, you're getting increases in performance that look very similar in terms of their profile to the increases in performance you get from the validly queued locations. What's really important here is that the difference between the queued and the unqueued locations is big and statistically significant from 30 milliseconds. Okay, so there's no evidence here of a gradually increasing queuing effect at the queued location. So what does this tell us? Well, it tells us that when you have both valid and invalid trials, so when you're confident you're measuring spatial attention, you don't get a gradual accumulation of attention at the queued location. In fact, attention seems to get to the queued location very, very rapidly within at least 30 milliseconds and pretty much stays there for the whole time. And that, I think, is consistent with the idea that Chiu and Leung's claim that spatial attention gradually accumulates at a queued location over the first 120 milliseconds of a trial is actually based on a misinterpretation of their data. So they're interpreting an arousal effect as the effect of visuospatial attention. So I think our conclusions are, firstly, that well, our main conclusion is effectively that Chiu and Leung are wrong. And contrary to common belief, covert exogenous attention does not gradually accumulate at a queued location. And if you're interested in more about stuff, perhaps about the relationship between that and the eye movement system, you can check out stuff on our webpage here, www.motorbiasproject.com. Thank you very much.